Cool. Thanks, Nick. Hi, everybody. Yeah, so I'm Jacob. I work at NVIDIA. At my core, really, I guess I'm an open source Python software engineer. Right? I work on distributed systems primarily. Before I was at NVIDIA, I worked at the Met Office working on HPC and distributed systems there for working with large data sets. Most of my focus at NVIDIA is on how can we enable folks to write code that runs on the GPU, but then grab many GPUs to scale out to their large data sets with whatever challenges they're having. Now I'm just going to swap my screen share over so you can see my slides. There we go. Right, shout if you can't see those. But the main department that I work in within Rapids, within NVIDIA, I guess, is called Rapids. Now, Rapids is a few things, but the kind of main place that you'll see it publicly is our GitHub page. Rapids is this suite of open source Python tools for building out data science workflows typically, but also kind of the traditional sciences as well. Anybody that's dealing with larger volumes of data that you're trying to process, do some analytics on, we're building tools that should empower that. Now, as well as building tools, we're also building or contributing upstream to other tools, right? So things that you may well know, if you're familiar with the PyData stack, the scientific Python stack, if you've done any kind of work with arrays in Python or Dataframes or any kind of machine learning, deep learning, whatever, some of these tools on this slide should be familiar with you. Some of these, especially that top layer, are typically GPU accelerated already. Many folks who are working on deep learning frameworks have already kind of taken the plunge into writing GPU specific code. But what we're trying to do is kind of bring the GPU acceleration lower and lower down that stack. So folks that are maybe doing data manipulation in pandas can now start leveraging GPUs, for example. And we do that both by contributing to those projects. Sometimes we'll build kind of alternative libraries that follow the same API. Sometimes it's just kind of educational stuff. We'll reach out to the community and try and share knowledge where we can. So to dig into the data science side of Rapids for a start, if you do any kind of data science workload today, you'll probably follow a path along these lines. You have to do some data prep. You'll load some data from somewhere. Maybe you've got some large CSVs or Parquet files or something which has got some data in. Use pandas to load that in, do some cleaning, do some manipulation. And then you hand off to some library to do some kind of training of some model to predict something, right? So whether that's traditional machine learning using something like scikit-learn, that might be deep learning with PyTorch, TensorFlow, etc. Maybe you need to do some kind of data format specific analytics. Maybe you've got a graph rather than a regular table. Maybe you're going to use Network X to do some stuff like that. And then eventually you're going to plot that to look at some results to, at the end of the day, make some business decisions. So Matplotlib tends to be popular, but there's a bunch of other plotting libraries in the Python ecosystem. And we've also got a little Dask blob in here. So Dask is one of the main bits of software that I work on, actually. It's a Python library for distributing Python compute across many CPU cores, across many machines. We'll come on to that later. So the goal of Rapids basically is to plug into all of these same slots with familiar libraries that people who know these things will already be able to just pick up and run with. So if you know how to use pandas, you can go and pick up CUDA, which is our kind of GPU accelerated data frame library. Follows the same API. You can import it, has the same methods take the same arguments. Everything feels pretty familiar, but it just goes faster if you have an NVIDIA GPU. Same for, if you know scikit-learn, you can use QML. If you do graph analytics, you can use cuGraph. PyTorch, TensorFlow, etc. are already GPU accelerated, so we just want to play nice with those. And then we've been working a bunch on visualization libraries where the visualization is rendered on the GPU as well. And we're trying to extend that Dask bar as well across to kind of allow you to scale out as many workloads as possible. So as I said, I work on Dask. Dask is kind of following a similar line to these libraries in that, say you do pandas work. If you want to use GPU acceleration, you can use QDF, and that will give you kind of a new library, same API, it'll go nice and fast on the GPU. Dask does the same kind of thing where there's Dask data frame. It looks and smells like pandas, has the same API, does the same kind of things, except it will leverage multiple cores in your machine, or you can set up a DAS cluster and it will use multiple machines within a cluster of machines. We have support for deploying on all sorts of different backends. You can run it on your local machine. If you've just got a nice modern CPU, you can run it on HPC, you can run it on the cloud, wherever. And the nice thing about these, because they're all kind of copying the same APIs, you can mix and match and use them together. So, you know, if you want to really scale out into a really large workload, you can use both Rapids and Dask at the same time to get this very, very powerful, very fast workflow. It just feels like Pandas or NumPy or scikit-learn, whatever you're used to using. And, you know, I have like an obligatory slide of how fast things go. I'm not going to labor over this. We benchmark these things. They go nice and fast. It's great. This is because GPUs do parallel compute. And if the kind of operation that you're doing is kind of, you know, is parallelizable, if you're doing the same operation to many, many pieces of data, GPUs love that kind of stuff, and you'll get some really nice performance increases there. So rather than digging into kind of all this stuff with Rapids and talking about high level libraries and how you can smush all your nice workflows over to go fast with GPUs, what I thought for this talk is I might just like drop all the way down to what are GPUs? What is that programming paradigm like? What's it like to write code in Python that runs on the GPU? You know, I've been at NVIDIA for 2 years now. When I joined NVIDIA, I like knew nothing about GPU development. I came in as this, you know, distributed systems engineer. I'm working on how do I grab lots of GPUs to use them together, and how do I handle the networking, and how do I pull clusters together, and how do I deploy different processes onto different machines. I'm kind of, you know, it's like a level above the actual compute that's happening. So I've spent time in the last couple of years skilling up on what are GPUs, what do they do? And I still consider myself like a novice in this area. It's not on the critical path of my job to know how to actually write really performant algorithms that run on a GPU. It's just my job to help people that do run those algorithms across many machines. So I quite like giving talks like this because I can try and be like an insider novice, right? I work for NVIDIA. I can tell you how GPUs work. Based on what I know. I can also be here to ask the dumb questions from the fancy engineers that really know what they're talking about, and hopefully kind of shed a little bit of insight into that. So that's the angle I'm going to come out from this. We're going to talk a bit about what this programming paradigm's like. I'm going to do some like live coding and show you actually how to run some code on GPUs in Python, and then we'll kind of wrap up. I'll do some kind of overview of those high level libraries at the end. But as I said, they're like drop-in replacements. If you know how to use pandas, then go and play with QDF because it's the same. And there's no point in me teaching you how to suck eggs. Just try it out if you have an NVIDIA GPU. So coming all the way back to like step one, what are GPUs? I mean, in my mind, it's just, you know, gaming things, right? They're cards you put in your computer if you want your computer to be good at games and shoot baddies and race cars and that kind of stuff, right? That's typically why I've bought GPUs in the past. The other thing that you tend to see people talk about GPUs is all this kind of machine learning, deep learning, fancy stuff that's going on where people are, you know, dynamically generating images and generating faces and telling you whether there's cats in pictures and all that kind of stuff, right? All the kind of very modern deep learning statistical stuff that you get coming out of places like DeepMind, they're using GPUs to accelerate that. And often as a user, when you're coming in to look at, you know, how do I do some of this stuff? You just get told, well, install some Python packages, install some libraries, you know, apt-get install some bits and pieces, and it's just going to magically run on your GPU. And don't worry about it too much. It's just going to go nice and fast, or at least it'll be performant to run these kind of workloads. And so I'm going to kind of dig a little bit down into what's actually going on and how can we write some pretty noddy code, but get it running on the GPU. So, you know, if you open up a PC, there's two different things in there, right? You have a CPU on the left here, which is just a small socketed chip, and you have a GPU, which is like a big card. Like, what's the difference between those two? Why do they have different form factors? And CPUs, we tend to talk about as like an individual item that is doing your processing, right? It's running your calculations on your machine, and a GPU is just there to add like graphics acceleration or whatever. But really, if you pull a GPU out, take the fan off, and actually have a look at the circuit board, it looks like a small computer, right? There is a socketed, or not a socketed chip, but there is a chip on the board that is the GPU. But then there's there's also some memory chips, and they're like the RAM that you clip in, but they're just kind of soldered on. And there's all sorts of other kind of components for doing power management and handling that memory management. There's like a big card, like what's it called? They're like an interface at the bottom, right? The PCI Express interface that you plug into your motherboard. That's effectively the GPU's networking, right? That's how it communicates with other things like the rest of the PC. So you've basically got two computers here, but what they behave very differently. So I'm going to play a YouTube video, and I'm not going to play the sound. I'm just going to talk over it. Shout if the video is not playing. Hopefully you can see the actual video running. But this is from the NVIDIA like YouTube channel, right? Which is why I can use it. But this is something that the Mythbusters guys put together a few years ago to kind of demonstrate the differences between CPUs and GPUs. So this first robot they're showing is a CPU, right? It's drawing a picture with a paintball gun of a smiley face by shooting one paintball at a time. Right? It does one operation after another. It does it efficiently. It's a great little machine. You could probably take that paintball gun off and put something else on. It's very robust. You can drive it around, you know. It's a very adaptive thing. Whereas this that they're showing now, this is a GPU, right? This is like a super fancy paintball gun, which has just got thousands of tubes. Each one of those tubes is loaded with a paintball of a different color. And it has one big button that they mash, and it's doing this large parallel operation, right? It's gonna, each one of these tubes is gonna fire a paintball out, and those paintballs are gonna hit in one go. And so that this machine is doing lots of different things, but lots of the same thing at exactly the same time, if that makes sense. Like there's a lot going on, but this has been specifically engineered to paint a very specific picture. And this is what a GPU is doing, right? So it paints the Mona Lisa in a big splat on the board like that. Now, yeah, let's watch the quick slow motion clip. There we go. Nice big paint splat, and then I'll move on. So this is a nice demonstration of the difference between these two things, right? CPUs are small, they're performant, and they're adaptive, whereas GPUs are a bit more big and sluggish, very specially tuned. And the main thing that they do well is they do lots of the same thing at the same time. But as you'll see in a minute, you can actually make those different things slightly more different than you would expect. And we'll get onto that when we write some code. But I've got a diagram here pulled from the NVIDIA programming guide, which shows you a bit of the actual chip architecture. So in a modern CPU, you might have 4 or 6 or 8 cores. Each one can do a calculation. It will have its own cache. It will have its own control for giving commands to that core to tell it exactly what to do. And then, you know, you've got higher levels of cache and eventually RAM that you can speak to. Whereas a GPU has got many, many, many cores. If you look at the spec for a modern NVIDIA GPU, it'll have a few thousand, they call them CUDA cores, right? These are the cores in the GPU which do calculations, but they have much fewer, like smaller caches and much fewer control registers. So you can give fewer commands. You kind of have to use them more uniformly. So when you're actually programming a GPU, one thing that I found was a bit of like a light bulb click for me is working with the GPU is much like working with another computer, right? If you're sat at your laptop and you're writing some code, you're writing some Python that works on some data, maybe you've got like a, you know, CSV file locally or something that you're doing some work with. If you want that to go faster on a nice big beefy machine, you're going to have to log into that machine, maybe you SSH to it or VNC or remote desktop or whatever. You're going to need to copy your data onto that machine. You could SCP it or FTP it or whatever you like. And then you're going to have to move your code over there as well. And you're going to have to make sure Python's over there. And then you're going to log in and you're going to run your Python script on that machine. And that machine will do something and calculate something, and it'll probably give out a result. And then you need to copy that result back to your laptop again. A lot of this happens over, you know, an SSH connection or something, but you're kind of connecting to this other machine and telling it to do things and moving data around. And working with the GPU is exactly the same. You can think of it almost like a separate machine. It hasn't got an operating system or anything fancy like that. So we have to live with CUDA. Now, CUDA is a few things, but one of the ways I like to describe it in this is CUDA is that connection. It's providing all these facilities for interacting with the GPU. It's you know, a way of communicating with the GPU. It's a way of moving memory to the GPU, and it's a way of calling functions on that GPU. But if you Google what is CUDA, you'll probably get loads of nice C++ documentation and lots of pages that tell you how to install lots of IDEs and debugging tools and C++ and C++ language extensions and all these kind of things. And it sends you off down a big C++ path. And I don't really know how to write C++. I sometimes write C++ for Arduinos for doing fun microcontroller things, but that's like hobby stuff. And that's fine. Like that is the traditional way of doing CUDA. But things are growing massively within that ecosystem. So as I said, the way I like to think about it is CUDA is facilitating us to write code that will run on the GPU. It's allowing us to copy memory and data to the GPU and then execute that code on the GPU. And if we think about it as facilitating that kind of connection, it will help as we move forward into Python. So let's do all of the things that it will tell you to do in C++, but let's do them in Python. So on my local machine, I've got a GPU. I've gone and set myself up with a nice Python environment. This is from the Rapids install page. Just tells you how to install Rapids with Conda. You can pull the Docker image as well if you like to go down that route. I've installed this because it gives you like the most complete like Python environment with all of the bells and whistles and tools and things. But what I'm going to do, I've gone and installed this, and then I've got a tutorial that I gave last week and a few months ago that I'm just going to pick out one chapter and run through one chapter of this tutorial with you, just so you can see actually what it's like to run this code. And if you look at the tutorial, I'll share the link in the chat, but if you look at the tutorial, we walk more through installing dependencies kind of one by one. So you don't have to install everything of Rapids in one go, but it's a pretty complete way of doing that. So I'm going to come out of my presentation now. I've got it as a backup, but I'm going to move over to, oh yeah, here's the tutorial. Let me go in the chat and just splat that in there. So I'm going to head now to Jupyter, and this is that tutorial, right? There's a bunch of chapters. I'm just going to do 2.0 from this tutorial, just so you can kind of see some stuff that's going on. I've also, just before I dive into this, I've noticed a few questions in the chat, so it might just be good to go over that. I'm just going to read through them very quickly to make sure there's something that I can quickly address. So yes, if you don't have a GPU, there are some cloud-based options. Google Colab tends to be the best place to head to if you want to grab a GPU to try some of this stuff out. You can also, grab it from whatever cloud platform that you like. I tend to, this is maybe slightly off the NVIDIA like party line, but I tend to say GPUs give people anxiety because they can be expensive if you rent them on a cloud provider, right? Say they cost like £3 an hour or whatever to rent. If you start one of those up and then forget and then go on holiday, you'll come back to a huge bill, and it makes people nervous, right? So platforms like Google Colab are great for trying stuff out. I think Kaggle notebooks have got GPUs as well you can play with. Like I have like a gaming laptop that I can install stuff on. It's quite a nice way of playing with things. But yeah, try any of these kind of ways of grabbing things, but try not to have too much anxiety about things. Just make a reminder on your phone or something to turn it off when you finish with it. Another question, does the QDF API have fallback to CPU? No, it doesn't. So if you want to do CPU, use pandas. If you want to do GPU, use QDF. Cool. Okay, so let's keep running through. I want to take a reasonable amount of time to go through this. So what we were talking about CUDA, weren't we? So CUDA is this way of interacting with the GPU, writing code for it and executing code. And in Python world, we have this really excellent package called Number. If you've not come across Number before, Number is a just-in-time compiler for Python, and it does real-time compiling of small chunks of Python to speed things up for you. Now, this is like, a CPU and GPU thing. You can import the JIT compiler from Number, and you can write a Python function. And if you use the JIT decorator on your function and then call that function, Number will compile that Python function down into a lower level thing using LLVM, and then execute it, and it makes it much faster. Like the first time you call the function, it has to compile and then run, goes a little slow. But if you're going to run that function thousands of times, you'll get some really nice performance increases because it's doing this just-in-time compiling for you. Number's really, really awesome. And one of the things it has is a CUDA package. So as well as being able to compile for the CPU, it can compile for the GPU. And it exposes all the like nice shiny CUDA things to us in a Python way. So we're going to work through this notebook, and we're going to write what we refer to as a CUDA kernel and run it on our GPU. So this is like one bit of jargon that will come up a bunch, is like a kernel. What is a kernel? So a kernel is just a function. Don't ever be like put off by the fact that all these people in GPU land, when you read forums and things, they're talking about kernels and you think, what on earth's that? Is that like the Linux kernel? It's not, right? This is just it's just a function. But there is a reason why we use different terminology, and that's because there are a couple of caveats when writing functions for the GPU, and they don't quite behave like functions for the CPU. So one of the things is that a CUDA kernel can't return. There's no kind of concept of returning when running code on a GPU, because all of these cores on the GPU are going to be calling this function all at the same time. So if you've got a few thousand cores, you're going to run your function a few thousand times. If they all return, you're going to get like a few thousand returns. And what do you do with those? How do you put them back together? How do you structure them? Like, that is hard to handle. And so we just don't. The way that we deal with that is we put some stuff into memory on the GPU. And then when we call our kernel, each kernel updates a bit of memory. And then at the end, when they've all finished, we can grab that big blob of memory back again. So we tend to very frequently work with arrays of data because it's very easy to kind of map memory addresses onto arrays. The other thing we have to worry about with kernels is we have to say how many times we want our kernel to run. Our GPU may have a few thousand cores or whatever, but we need to specify, I've written this function, I want it to run 10,007 times. You know, you have to be very specific with how many times it's going to be called. It's a little bit like doing stuff in a for loop, but you just have to be upfront about saying, I'm going to call this function and I'm going to call it this number of times. You can call it way more than you have cores on your GPU. And so the way that we handle that is we have this whole idea of grids and blocks and threads. And these are more words that they get a bit muddy and maybe a little overwhelming when you're working through these things. But we have this term of a grid. This is the number of times I want this function to be executed. Now, if I want my function to be executed 2 million times, I don't have enough cores to do that. So I'm going to kind of need to do that in pieces, right? I'm going to need to call it, you know, saturate my GPU, and when it's finished, I'll go to the next and go to the next. And so these next sections are called blocks, right? We do things in blocks of, you know, 1,000 processes or something. So if I want to call my function 2 million times, I'm going to say, well, I'm going to do it in blocks. I'm going to do it in blocks of 512 because that's a nice round binary number. And I need to work out, well, how many blocks of 512 do I need to do 2 million? And so you have to do a bit of maths to work out how big are my blocks, how many blocks do I need, and how, you know, to make up what, you know, my overall grid size. Now, this is like a hard thing to get your brain around a little bit. It's a bit of a paradigm shift. It took me a long time to kind of get familiar with this. So don't worry if everything I just said is French. Just have a look at these diagrams and hopefully things will make a bit more sense in a minute. Now, one of the things I said in that is we have to decide how big our blocks are. And like, I've given you no information on how to do that. So if you go and have a look at the nice number documentation, it says, choose a number between 128 and 512 and make sure that it's a multiple of 32, because that's the way things work. And so this is just because of the actual hardware has this it does things in lots of 32, but GPUs tend to have somewhere up to about 1,024 cores in kind of older revisions. So don't worry too much about why we make these choices. Often what we do is say, choose a number like 256, try it out, get used to it, and then, you know, change that number to 512 and benchmark and see whether you've got, you know, different performance characteristics based on your algorithm. But just pick a number and we'll run with it just to get us going. So for this whole tutorial, I just used the number 128 because it's the first one the number documentation suggests, and that's fine. So we're going to do that and everything will be okay. So let's actually talk a bit about parallel code in Python. Now, writing some very pure Python here, the closest thing I can think of in pure Python to calling like a GPU kernel is doing a list comprehension, because you're writing like one expression on one line, like this one here with the square brackets. You're saying, call my function on I for I in data. You know, it's a for loop, but it's like wrapped up into one line. So I'm kind of running this one line, and that is doing effectively a parallel operation. So I've got this little bit of code here where I've got the numbers 0 to 10. I'm going to write a function, which is just going to return those numbers again. And then I'm going to call them kind of in a parallel way using a list comprehension. And if I run this, it returns me the numbers 0 through 9, which makes sense. And what we're going to do now is we're going to morph this into a CUDA kernel that's going to run on our GPU. So the first thing that I said is we can't return, and I've got a return here, so we need to get rid of that. So what we're going to do is instead of returning, we're going to have another empty list here called output. And instead of returning, we're just going to append our number into that empty list. So same thing again, we've got the numbers 0 through 9, and we've got a little function, and we're going to call that function with a list comprehension, but just instead of returning, we're going to put them up into that list. So if I run that line, we can see it just outputs 0 through 9 again, because we've stuffed all those numbers into our output list and then had a look at it. Now that's great. There is one caveat that I haven't mentioned, though, is that GPUs are a little bit more primitive in the way that we handle memory structures. And so we can't have nice things like mutable lists. We can't have a list that we keep adding things to. We can mutate the list, but we can't mutate the length of the list. So we're going to have to create a fixed length block and update things in that. And that's fine. We can do that. We can import our nice friend NumPy here just to make life a little bit easier. And we can use NumPy instead to make an array that is the numbers 0 through 9. And then we're going to make another array, which is just 10 zeros. It's just an empty array, but this is now something we can tweak and add things to. So we've changed things a little bit here. The function here now, instead of appending to the list, we're updating an index in our array. And that index is the index corresponding to the value that we've been given. And so we can run this through exactly the same. Oh, I forgot to import NumPy. I do that every time I run this notebook. Okay, and this outputs us this list of the numbers 0 through 9 again. I know it's turned them into floats, so we've got some decimal points in here, but it's done exactly the same thing. We've created some data. We've created like an empty output array, and then we've run some code to just populate that output array. And now we have something that is actually a kernel. This foo I equals, I is a kernel in the fact that it doesn't return and it updates stuff in memory. And so we can run this on the GPU. Let's import CUDA from number and actually do a couple more manipulations to it to run this on the GPU. So my data construction is the same. I've just got my array of 0 through 9, and I've got my empty output array. I've got my foo function, and I've decorated it with CUDA.jit. Now, this is telling number, please compile this into a CUDA compatible blob and hand it to the GPU and ask the GPU to do the thing. And now I'm not passing it I here. I'm having to pass it pointers to the array and the output array. And this is just because this function is on the GPU and it knows nothing about my global space and my global scope. So I'm actually having to pass it those pointers to just say, here are the arrays. But where's I gone, right? I's kind of disappeared. And what we're doing here is we're doing this nice little call here that says I equals CUDA.grid of 1. And what this is doing is saying, I'm going to call this function 10 times on my GPU because I want to update 10 bits of data. Each function that while it's executing can say to the GPU, which function am I? There's 10 of us. Which call am I? And each function execution is given a unique index when it's running. And this is awesome. This is why GPUs are way more flexible than I kind of really realized until I started learning about this stuff, because each function as it's executing, say I call this 1,000 times, each one can say, well, which one am I? And it goes, oh, you're number 10. And it's like, okay, well, I'm number 10. I can add if I'm number 10, go and do this. And then if you're number 12, go and do this. And each function can like diverge hugely here, right? They can do whatever they want completely independently. And you've now got thousands of cores all doing separate stuff. And that's awesome, except when the CPU calls this function, it has to wait for them all to be done. And so if they all diverge too wildly and one of them takes forever or crashes or something, the whole lot will crash or kind of lock up. So you kind of have to make sure that whichever directions they go off in, they're doing roughly the same thing that's going to take roughly the same amount of time. We're talking about like nanoseconds here, right? As long as they're kind of within a few nanoseconds of each other in terms of execution, you're going to be fine. So we're going to grab our index here, and then we're going to update our output array with our index just to fill it with some stuff. And now we're going to call our CUDA kernel. Now you notice this call is a bit strange. It's a function, but then it's got some square brackets, which is a bit weird. And this is us configuring our grid, right? Us saying, I want one block of 10 threads. This is us just telling it how many times to call it. And the way that number exposes this to us is by using square brackets in our call. So we say call foo in one block of 10, and here's your arguments, here's data and output. And now if we run this, I don't know if the screen capture shared that nicely, but my GPU utilization graph like flickered ever so slightly because my GPU just did a thing. And so I have my nice array of the numbers 0 through 9, but my GPU did that this time instead of my CPU. So, you know, I've still written pure Python here, but I've made my GPU do a thing rather than making my CPU do a thing. Now this is, you know, this is a silly example. Having my GPU put the numbers 0 through 10 in an array isn't a particularly hard calculation. So let's do something a bit bigger. Let's take 30 million random numbers, and then let's double those numbers. We'll have the GPU double these. But first, let's have the CPU double these. So I'm going to run this. I've got my 30 million numbers. I've got a little kernel here, which is just doubling each one. The CPU's here chugging through one after another, doubling it. And I've now got my output. That took 10 seconds to double all of those numbers, my 30 million numbers here. Now, I can do exactly the same, but on my GPU. I've still got my random array. I've created my output array. I've had to calculate. I wanted to do this 30 million times. So I've had to work out, well, if I've got 128 threads, how many blocks do I need? I have to do a bit of maths to work out how many times to call the function. Everything else is pretty much the same. And that took 1/4 of a second. So instead of taking 10 seconds, I'm now 1/4 of a second because my nice parallel GPU did this all in one big go. Now, I'm going to kind of skip through a little bit, just given time, but that 1/4 of a second is actually quite a long time in GPU context, because we had to copy our big random array of numbers from our CPU to our GPU, do some stuff and copy them back. A number was very kind and did that for us. We gave it a NumPy array that's on the CPU. It's done that copy and it's done that copy back completely transparently. And that's great until we want to do lots of things on the GPU. And then numbers just going to be copying stuff back and forth and back and forth and back and forth. Every time we call a kernel, we're going to be moving memory. So the other thing we need to do, or need to think about doing, is let's manage our memory ourselves. And it gives us functions to do this. So we can say CUDA.toDevice and give it our array. And this is us explicitly saying, I'm going to copy some memory from my CPU to my GPU. I've now got this new variable, which is just pointing at some data on my GPU. I can also make my empty array over there. Now, if I run my doubling function, it takes 15 milliseconds. Right? If I run it again, just because of weird caching things, it now takes 700 microseconds. Right? We've gone from 10 seconds on the CPU all the way down to, you know, less than a millisecond. But my data is still on the GPU. There is some penalty to moving memory around. So I also have to say, oh, I'm going to copy it back again. And I can do copy to host. So this is kind of demonstrating what I was saying about CUDA is this facilitator of running stuff on the GPU. It lets you move memory around, it lets you write functions, and it lets you execute those functions all within kind of regular-ish looking code. You have to do some weird stuff with square brackets, and you have to do a bit of maths to work out how many times to run things. But that is running some pure Python code on the GPU using a couple of excellent Python libraries. Now, I put the link to this tutorial in the chat. There's like way more to this. Like the next one, we like, let me just run this really fast if it does it. We're like blurring images, which is way more interesting than doubling random numbers. We take like the number logo and run through our own like custom blur, Gaussian blur kernel, which gives us a nice blurry image. So if you want to like go and grab these notebooks and play around with them in your own time, I recommend it. It's quite a nice introduction to running parallel code, and the fact that if I've got an image and I want to blur it, I can operate on each pixel independently. I'm doing the same thing to each pixel. I'm blurring each pixel, but I can work on a whole image in one go and do it really nice and fast. So I'm going to swap back to my presentation now. After that, that seemed to, nothing crashed then, which is good. So let's pop back here. I said I kind of wrap back around to Rapids and the high level things. So to kind of come back to the high level APIs, if you don't really want to get too dirty with writing all of that code and worrying about threads and blocks and grids and calculating things, you can use these nice high level of implementations. So if you're used to writing NumPy code, you can go and pick up CuPy. It imports the same, you just import CP, and then you can basically swap out all your NumPy calls for CuPy calls, and it will handle all of this for you. You can make random arrays, you can see how big they are, you can calculate all the kind of standard array operations you would do in NumPy, you can do them with CuPy with the same function calls. And it will just use this acceleration under the hood to give you faster results. And if you want to really go far, you could import CuPy as NumPy and then just use it in existing code bases. You might run into some memory copying challenges that you have to be a little aware of the fact that memory is flying about all over the place, but it will give you an accelerated experience. The same with Dataframe libraries. If you're used to using pandas, you can go and import QDF. You can make Dataframes the same. You can do all the same kind of group by operations, merge, filters, whatever you like. And all of this will just run on the GPU for you, and it will be dispatching these kernels on your behalf. And so, this is great. If you've got, when you're doing Dataframe stuff, it's quite common to talk about the New York taxi data set as like an example data set that folks are aware of, right? It's a big table of all of the taxi trips taken each year. The New York City make it publicly available. One of the things it gives you is the latitude and longitude of pickup and the latitude and longitude of drop off. Well, maybe you want to calculate the distance between between pickup and drop off. That's something that isn't in that data set, but you can calculate easily. If you've got 100 million rows in your data frame, the GPU can really nicely chug through that, right? Each core of the GPU can be calculating an individual point-to-point distance. That will take, some amount of time, and it will be a different calculation for each point. But because the GPU is doing this big batch parallel work for you, it'll work through calculating those distances much faster. So QDF is great if you want to do that kind of thing. And then we've also got, cuGraph for doing graph analytics and QML for doing machine learning. Now there's another example in that tutorial where there's a data set in there, which is folks who have diabetes and some other properties about them, their BMI and those kind of things. And it walks you through an example of reading in that data, doing some massaging to it, and then training a model to predict whether or not somebody has diabetes based on those properties. And you can do that in scikit-learn, and that's great. But then you can also do that with QML, and it will just accelerate that training, and it'll accelerate that inferencing by making use of the GPU. So it's all in there if you want to have a dig through that material in your own time. The last thing I kind of want to just touch on here is, as well as building libraries, we care a lot about interoperability with other libraries. So, we've looked a bit at Number, and I've talked about CuPy and other things, but what if you're doing stuff in PyTorch? What if you're doing stuff in other kind of GPU accelerated Python libraries in this space? We try and make it really easy for you to be able to move your data between these libraries in as efficient way as possible. And so we have a couple of standards that we help implement in a few places. One's called DLPack and one's called CUDA array interface. And these allow you to, if you have a tensor in PyTorch, right, which is just a big array of numbers, and you want to convert that to a CuPy array, in memory, those are identical things, right? They're just arrays of numbers in memory. But they're kind of wrapped up in a different high-level Python object. So these interfaces allow you to just cast one array type to the other, and it won't copy the data on the GPU. It'll leave the array alone. It will just create you like a new set of clothing for that array, so it then fits into whichever library you want to switch to. And this is great because often you'll load data with one library, you'll clean it with another, and you'll train some machine learning model with another. And so being able to like swap between these different tools is really useful. Yeah, let's skip over that. And so, yeah, that's kind of me towards the end of the talk. We took some concepts here and applied them. We had a look at some Python code. We wrote some pure Python. We smushed that into some kind of GPU flavored Python, and then we moved it to the GPU and we executed it. So hopefully that's given you a bit of an insight into how you can get stuck into running stuff on the GPU. Now at the end, I've just seen another question pop up. So let's have a look. Oh, it's Nick. Apache Arrow is shown on the schematic. Could I explain how Apache Arrow fits in? Yes. So Apache Arrow is a great project for in-memory array representations for tabular data. And we use it a bunch under the hood in QDF specifically for handling our in-memory representations. And that's part of what allows us to swap from one memory type to another is this consistency. Now, as I say, I don't get super deep under the covers into how the actual GPU libraries work. I'm more at running them on many GPUs. So I can't go into huge detail about Apache Arrow, but if you're interested, go and have a read. It's a great project. There's some great folks working on it.
Okay, brilliant. Thanks, Jacob. Maybe people could unmute and show their appreciation. Thank you. There's no barking dogs or parrots this week, which is a disappointment. So are there any other questions? Maybe if people want to unmute and ask any other questions, then this is your opportunity to do so. Anything from anyone? No, no other questions. I was wondering as to the data movement comes as a penalty, and dig into that. And it's not clear to me currently where the remote the using remote GPUs comes in. Is that because we've been working there with a local GPU? Could you just explain how you would then make the jump to using remote resource?
Yeah, I mean, so I mean, all the examples I ran through there are all like synthetic data, right? I was generating the data on the CPU and then moving it to the GPU as I was calculating it, right? But if that data is on a disk, it's like another step further away from where you are. So it's remote GPUs. I mean, you can grab GPUs wherever you want, right? They're nice performant, but it's a hardware that you can grab from the cloud. But it matters where your data is that you're going to be working on, and it totally depends on what kind of workload you're doing. I mean, if you're a bank or something, and you're trying to look through folks' accounts to calculate their credit score or something, that's a reasonably large amount of data, but it's not insane, right? You can upload that to S3 or wherever. If you want to use GPUs on Azure, on AWS, you can move it to S3. If you want to use it on Azure, you can move it to their blob storage or whatever. And so loading data into the GPU, you can do stuff from wherever. I think one thing that is worth noting is GPUs are super fast, right? It's depending on what you're trying to calculate on them. It's sometimes hard to feed them enough data fast enough. You know, if you're trying to do some really intense machine learning model, then you're going to really be pushing that GPU and the data is going to be flowing in piece by piece. Whereas if you're trying to take a climate model run and calculate the mean over a field, that's easy for the GPU, right? Calculating a mean of like a few terabytes of data is going to be done very quickly. And your hard drive probably can't push data into the GPU fast enough to actually fully saturate the hardware these days. And especially if that data is in S3 or something, and you're having to make HTTP calls and the CPU is busy doing SSL handshakes to download files, the GPU is just going to be twiddling its thumbs. So depending on what you want to do, it's good to move data to high-speed storage if you can locally to wherever your GPU is, and that is, you know, something you have to pay some upfront cost to doing. But it just totally depends on your workload. If you're doing hard things with small data, then it's easy. Whereas if you're trying to do easy things to big data, it's definitely a challenging thing. We're doing a bunch of work at the moment on something called GPU direct storage, which is pretty new. We haven't done a huge amount with it, but GPUs now, through the CUDA driver, can read directly from an NVMe SSD that's plugged into the machine. They're both connected to the PCI Express kind of backplane. They don't have to speak to the CPU at all. The GPU can just read from disk. So you get, you know, huge performance increases there. This is all super new. It's used in some HPC environments. We're trying to look at integrating with the Python stack, but that's kind of a work in progress. The video game side of things is starting to look at, can it load textures and that kind of thing from disk straight to GPU.
And that seems to make sense from the point of view you were saying that the GPU resembles a computer. Obviously, it's using the storage of that computer, so presumably bypassing that to have its own direct connection is a sensible way to go.
Yeah, exactly.
So that's really to do with the velocity of the data, isn't it? And that mismatch between slow storage and fast GPU. I had another question around why specifically Python in this case. Is it because of the existing ecosystem and it's therefore leveraging the existing ecosystem for these use cases?
Yeah, it's going to where the users are, basically. You know, folks, tools like PyTorch and TensorFlow are already very popular. You know, we're specifically targeting data science and traditional sciences here. Data scientists seem to be very much either in the R camp or the Python camp, but there seems to be a trend towards Python, and so this is just us trying to meet them where they are.
Sai, do you have a question there in the chat? Do you want to ask that question?
Yeah, but I think it was just answered.
Okay.
The M1 hardware, it shares the memory for CPU and GPU. Do NVIDIA have any CPU architectures that they combine with GPUs to do the general lifting, and then the GPU does the specialist bit?
Yeah, so I mean, if you look at something like the M1, that's like a full system on a chip, right? The CPU and GPU are on the same silicon die, and they just have access to one set of memory. There are NVIDIA chips like that. There's the Tegra series of chips that you'll find in the like Jetson series of hardware. You'll find it in the Nintendo Switch. You'll find it in the NVIDIA Shield TV streaming box. These are like ARM-based processors with NVIDIA GPUs all on the same silicon. They have the same access to GPUs. But more and more so in machines. I mean, like if you look at games consoles as well, they tend to share memory between the CPU and the GPU. And that's a pretty common practice. There are different performance characteristics between the type of RAM that you put on a CPU and the type of RAM that you put on a GPU, and they benefit different types of workloads. And so when you have a system with two separate sets of memory, you're kind of choosing specific memory that's more tied to the kind of workload that you're doing. Whereas when you're kind of moving to a coupled system, you're kind of losing something there in terms of that flexibility, but you're gaining something in terms of the speed. And so if you're doing something like rendering video games, it makes a lot of sense to share memory. Whereas if you're doing something like general purpose workloads on your computer, like opening emails and things, and also trying to play videos and maybe trying to render videos and trying to play video games and trying to do data science, having two different characteristics of memory can be beneficial there as well. But I don't know, watch this space. There's lots of interesting things going on with these chips.
Without wanting to open a bit of a Pandora's box, I was wondering whether you could just outline the difference between a GPU and an IPU, and whether the approaches that you've been talking about tonight are also relevant for an IPU.
Yeah, sure. I mean, like an IPU and a TPU and a whatever else PU chip that you see floating about those chips are they're coming out of these companies that are trying to build very bespoke hardware. You know, if you look at Google, they're building their TPUs, which are very, very well tuned for TensorFlow workloads. And they're kind of designing the silicon hand in hand with the software. If you look at what Amazon has in terms of their chips for running Alexa and those kind of things, they're building like from the product all the way back to the silicon. Whereas NVIDIA's coming at this from the, you know, traditionally building parallel cards for doing gaming, but kind of more and more moving into the general purpose computing. NVIDIA's building parallel processors effectively. They're much more generic pieces of hardware with a whole bunch of stuff in there for doing specific things, right? There's all sorts of like gaming type things written into the silicon, and more so as we're getting down the kind of CUDA compute line, there are kind of other function calls and algorithms and stuff that we're seeing accelerated in hardware. This is why if you have a look at our documentation and that tutorial I shared, Number, I think, supports GPUs from like the 6 series onwards, the NVIDIA 6 series, whereas Rapids we support from the 10 series onwards. And that's because of advancements made in the silicon to specifically speed up some bits and pieces. So like GPUs are like a much larger piece of silicon for doing all sorts of general things, whereas these things like IPUs and TPUs are smaller, more kind of targeted bits of silicon. They're almost down the end of like ASICs, right, where you're designing a piece of silicon for a very, very specific use case, right? All the Bitcoin miners want chips that just do the number crunching for Bitcoin, and they don't want all the rest of the power consumption and things that go with it. So you've got this spectrum where you've got CPU at one end and TPU at the other and GPU in the middle, and you're kind of getting more and more specialized as you head down that path. And yeah, there's just a lot of machine learning focused chips kind of coming out at the moment. Yeah.
Okay. And how important is open source? I know you there in your schematic you called it an open source stack. So could you just first of all say the NVIDIA line of open source, and maybe like if you've got a personal comment as well, that'd be useful.
Yeah, sure. I mean, the tools that we work on are open source Python tools. And this is, I think the tagline on the Rapids website, if you go and have a look, is like open GPU data science, right? We're building tools. If you go and have a look, you can see the C++ that makes up all of these libraries. You can see the Python layers on top that make up these libraries. All of this stuff is open. And the reason it's open is because we want to build the best software and facilitate people using NVIDIA GPUs as much as possible, right? So if the best tool for the job in data science is an NVIDIA GPU, that's great. That means people are going to go and buy NVIDIA GPUs. So it's in our interest to make the software as kind of open and free and available, and with many eyes, bugs are shallow, that kind of thing. And then, yeah, as you get down the stack, eventually you're going to hit some proprietary layer, right? At the very bottom of the stack, there's a piece of silicon that somebody at NVIDIA, or lots of people at NVIDIA, design and manufacture, and you have to go and buy in order to do this. And at some point you have to draw a line of where does that proprietary level stop. I think if you look at regular PCs and things, you kind of dig all the way down to, like, if you're running Linux, you're going to go all the way down as far as like the BIOS on the motherboard. That will be proprietary. You're not going to get the BIOS code from anybody, or going down through the bootloader and that kind of stuff. Whereas with the GPU, you're kind of going all the way down to CUDA, right? CUDA is that proprietary line where everything above that is open source and everything below it is proprietary. So if you want to use these tools, you have to buy an NVIDIA GPU, and that's the intention here. But it is all open source. If you want to work on these tools, you definitely can.
Gotcha. Okay, that's really useful. Great. Okay. Well, I think I'm exhausted for questions. Any last questions before we close from anybody? Nothing. Okay. Gone. So if I will just close up. So this has been recorded. All our videos are up on the website. Sorry, a bit of an echo there. So if you want to catch on replay, then please do so. The next event on 3rd of December was actually a Friday, so we're not going to be doing the first Thursday. It's the Friday the 3rd. We've got Andy Mott from Starburst talking about the data mesh. So please do join us for that. And many thanks, Jacob, tonight for that really engaging talk. Very good, very interesting. And we will be posting all the resources under the video. So if you want to take a look at any of the other tutorials, then we'll be posting all the details on there. So thanks very much. Thanks for watching, and we'll catch you again another time. Thanks a lot. Bye-bye.